So today we are switching topics. So we are looking into a topic. So till 2019, when I used to teach this, I thought that this was not relevant for our modern society. And then in 2020, COVID happened, and we realized that this topic is still very relevant. Okay. So what is a epidemic? So why are we considering this topic as part of a course on network science or a course on social network analysis? This is because for some diseases they are spread um, not by contagion but by other kind of ways. So for example, cancer, for example, is not relevant for network science or SNA. But diseases like COVID are very relevant because they are spread not only by the pathogen, but they are spread because of the contacts people have. Okay, so when you want to tackle pandemic like COVID, so it was not only the medical personnel who were looking into this, but there were, if you had looked into the papers that time, there were a lot of statisticians and all who were also looking into this problem. And what they were trying to do, one of the main things was to predict what is the course of this disease. Okay. So epidemics that are caused by contagious diseases. So these are the ones that are of interest to network science and SNA. Okay, so these are caused by the biological pathogens and can be of different kinds. It can be a sudden explosion, or it can persist um, for a long time at low levels. So, for example, things like dengue, they occur every year at some time, and then there can be sudden flare-ups that can happen, like it happened with COVID, or it can be cyclic patterns. So, dengue also can be cyclic. It generally occurs during the monsoon season and so on. And of course, we know that it can be devastating. We saw, so even before, so we had a plague that killed 20% of Europe in the 1300s, and we used to think that this kind of epidemics cannot happen anymore, and then COVID-19 happened. So why are we studying it is as part of network science or social network? Because the epidemics are determined not only by the pathogens. So the pathogens are the ones who are spreading the disease. So they can, and the pathogens determine the contagiousness. Some pathogens, they may not make contagious. They may not pass from one person to the other. And but some pathogens are contagious, as we saw in the case of the COVID-19 virus, and also the length of the infection. So that also matters. If your pathogen does not cause maybe a 2 or 3 day, that may not be very devastating. And of course, epidemics, our focus of interest is the social network that causes the epidemic. And so how is the social network created for an epidemic? So it again depends on the pathogen. So some viruses, they spread by air. Okay, so if they spread by air, then there are a lot of links in the network. So as you are, anyone of us can spread it because we are all in contact with each other in case of airborne pathogens, and therefore COVID-19 was so devastating. Or it can be the, if only if you are in close contact, then it will spread. Then it would be a sparse network. It won't be something that will spread in a wider population. And the interesting thing is, just like you can study viruses that are causing diseases to human, similar kind of study can also be done for computer viruses. But we are not looking into that in this class. Okay. So first, let us look into a very simple social network, which is a tree structure. So we have one person at the top who has got the disease, and he is connecting with other persons, and those persons are also connecting with other persons in a tree structure. So we are considering a very simple structure at first. So how the disease will spread, there are determined by two things. The first is contagion probability, what we call contagion probability. And what is the contagion probability? Contagion probability means that, and that is different for different diseases. It means that if I come in contact with a person, what is the probability that I will spread the disease to the person? So if it is zero point 0.8, if the contagion probability is 0.8, that means 8 out of 10 times I will be spreading the disease. Or if it is 0.4, then it is lower. So maybe only 4 out of 10 times I will spread the disease. So that is a key parameter. And the other key parameter, of course, is the number of people I come in contact with. Okay. So if I come in contact with more people, I will have more chance of spreading the disease. Okay. So this contagion probability is different for different viruses, different for different pathogen, and that is key, because if the contagion probability is high, then the disease will spread, because there is a greater chance of the disease spreading. And so, for example, if it is 2/3, then it is very high, it will spread to the population. But if it is low, then the disease will die out. Okay. So if you had read the papers during the COVID-19 pandemic, you would have seen people talking about a number called reproductive number. Okay. They were telling, oh, the reproductive number is high, reproductive number is low, and so on. So obviously they were looking into a more complex network, but even for this simple network, what is valid for a complex network. So reproductive number is Q into D. Okay, the contagion probability into number of people you are in contact with. And if that number is less than 1, then with probability 1, the disease dies out after a finite number of waves. And if this number is greater than 1, then the disease will persist for a long time, infecting at least one person. From each person that is infected, at least one other person will get infected. And if it is near 1, a small change in K can have a significant change in the effect of the disease. So you will see that people were talking, the statisticians were talking about reproductive number. They were telling for some cities reproductive number is becoming much higher than 1, and they were getting concerned. So this number is a very important number in the study of the disease. Okay. And so how can you reduce this reproductive number? So obviously there are two parts, one is Q, one is D. So for controlling Q, you can, so Q is the probability that the disease will spread. Okay. And so for that you can, for example, have better sanitary practice, so that one person who is contacted won't. Obviously the pathogen itself will have some characteristics for Q, but you can have better sanitary conditions so that the germ won't spread. And of course D, the number of people an infected person gets comes in contact with, that can be stopped. Yeah.
So what is K and P?
So K and P are the just two synonyms for the same things. Okay. So K, you can call it K and P. P for the contagion probability and K for the number of people, or you can call it Q or D. So both are synonymous. Okay. And D or K is the number of people you can come in contact with, and that you can stop by, for example, quarantining people. We had those lockdowns, so that was also meant to reduce D. Okay. So in our case, for this small thing, it is this reproductive number is only relevant for the trees, and there are other more complex models. But for in our case, in some situations, even if the reproductive number is more than 1, the disease may not spread, or if it is less than 1, still the disease may spread. Okay. So here what happens is the reproductive number is 2/3, and but here the disease will tend to peter out after some time. So the structure of the social network also matters. Okay. So how so this there is this field called epidemiology. So this is it's a combination of statistics and also medical things. So that studies how a disease spreads. Okay, and so one of the things that statisticians were trying to do was to predict when the disease can stop. So if you see around 2020 June and all, there were some studies coming out of IIT Kanpur which they said that the disease will in India will stop by October, and of course that was a very wrong prediction that happened. And how do people do this prediction? And so they do it based on various epidemic models that have been created. Okay, and the simplest so for these epidemic models there are two things that are important. One is the birth rate, probability that an infected person will, here birth rate means the person who is a new person gets infected, so that is meant by birth rate here. Okay, so a person that is infected will affect another person that is not infected. So the birth rate beta, so it's the probability that a infected neighbor attacks. So for example, if N1 is a person who is already infected, then with probability beta he can infect another person N. Okay, so that is the birth rate. And another probability is the death rate. And here again the death rate is the not of the person but of the virus. So probability that the infected node heals. Okay, so a person who is infected N, it's a probability delta that that person will become healthy. Okay, these are two important viruses that parameters that we utilize for studying this propagation of a virus. So people have come up with various models, okay, to say how we can model. So just like in any case, so for any prediction, what you do, you have a model with various parameters to figure out how that thing will spread or something. So the simplest model that was created was called the SIR model, the SIR epidemic model. And what it says, individual, so it has the person can be in three states in this model. One is susceptible. Susceptible means that a person is not yet he is healthy, but he is prone to get the disease. So initially, when COVID started, all of us were in a susceptible state because any one of us could have got the disease. Then the thing is infected. Infected means that the person has got the disease. Okay, and the final state is removed. That means a person has already got the disease and has recovered from the disease. So those were the three parameters, and the progress of epidemics is controlled by the contact network, by and the and of course the p, the length of the probability of the contagion, and also the t, which is the length of the infection. So initially some nodes are in I state and others are in S state, and then each node V that enters the state remains infected for a fixed number of steps T1, and during each time T1 step V has a probability of passing the disease to each of its susceptible neighbors. And after T1 step, the node V is no longer infectious or susceptible, so we have it in the removed state. Okay, so we have the susceptible, infected, and recovered. So those are the three states: recovered or removed. And so what you have is the person who is susceptible with a probability of beta, he can make a person infected, and a person who is infected with a probability delta can recover. Okay, and so assuming a perfect mixing of the network, we can have this formula ds by dt. The number of people who are susceptible would be minus beta si. So people, it is a negative sign because people are moving out from the susceptible state to the infected state, and then recovered is dr dt is si, delta I, and di dt is beta si minus delta I. Okay, and so you see there is a three graphs ST, RT, and IT, and these are the graphs that people try to utilize for figuring out how this disease will spread. So whether the disease will peter down or whether it will continue, how long it will go on. So these are the graphs people use. Okay. So SIR model was the one of the first model that has been created, and obviously it's a simple model. So what do you think are some of the problems with this model for looking into a real world disease?
It assumes that one person can infect everybody else because they are assuming that it is a complete graph. That is not a good approximation.
But why not? So if you are you come in contact with someone, you can definitely spread the disease to someone, and they have created a probability for that. If I come in contact with you, I have a probability of spreading the disease. Okay, so
Once one person is susceptible and gets the disease, they're no longer susceptible. But in COVID, we saw that
exactly. So that is one problem. So one problem is that we assume that you cannot get here. Once you have the disease, you cannot get the disease again. So that is true for some diseases like chickenpox and others. It is true, but it is not true for a lot of other diseases, including COVID. Okay. So we will see other models that have been created for that. Okay. So this is a SIR epidemic model, how it's spreading. So initially we have 2% Y and Z that is infected, and then they spread it to X and U and so on. So this disease is passing through multiple nodes like this. Okay. And so you can also have so that is obviously the spreading is a uh, dynamic thing. Each time some people get infected, but suppose you knew beforehand that okay, these are the people who will be infecting these other people, then you can create a static view of the models. If you knew beforehand that Y will not spread the disease to Z, but Z will spread the disease to X and Y, so you can have those links in bold to figure out how the disease will spread. Okay. So as I said, as you said, that some diseases you can get affected again and again, and for that another model was created called the CIS model. Okay. So what does the CIS model say? That there is no remove state. Okay. So after a node has been done with the infectious, it cycles back to the susceptible state and is ready to catch the disease again. Okay. So initially some nodes are in the I state and all others are in the S state. Okay. Each node V that enters the state remains infected for a fixed number of steps, and during each of these T steps V has a probability of passing the disease to each of its susceptible neighbors. Okay. And after T1 steps, the node V is no longer infected and it returns to the S state, susceptible state. Okay. And so here we have two states only: susceptible, infected, and susceptible. Cured nodes immediately became susceptible, and we call the virus strain to beta bus S. So this is the transition diagram. Okay, for this. So here also you can create a graph for how the disease is spreading. So you have the infected and the susceptible state, and this is a good way. So for example, flu is a disease that can come back again and again. So this is a good way of measuring that. So again, assuming perfect mixing, we can have the formula for dsdt and didt. Okay. So in a say epidemic graph, the nodes decrease over time, because what happens is once you have the disease, you cannot have the disease again. So the social network will decrease over time because nodes that have got the disease can be removed. And while the CIS model can run for a extremely long time. So for example, flus have been going on for time immemorial. Okay. And at a particular critical value of the contagion probability, CIS epidemic on the network will undergo a rapid shift from one that dies out quickly to one that persists over a long amount of time. Okay. And the CIS model can be converted to the SIR model by a expanded contracted network. So what you can do is, once a person has been got the disease, you create a new copy of that node, and that way we can have the same model representing both SIR and SIRS. Okay. But if you look into this model, if you look into the CIS model, that has a lot of problems. So it's a very simple model because there are other states the people can be in. Okay, so if you look into any disease, so for example, uh, they can. So we have this notion of quarantine, right, where we have some people in quarantine. Then we have this notion that some people may be not at all exposed to the person who has the disease. So something that you had said that uh, I may not come in contact with a diseased person at all. Or the other thing is I get come in contact with a diseased person. So there it should be a difference between a state where I have not come in contact with someone or I have come in contact with someone. Then there is, of course, the thing that some people will have recovered, but obviously some people unfortunately can pass away. So there can be various other things. And then there is a thing of vaccination. So if someone has the vaccination, how do we take care of that person? So what people had done is so these epidemiologists, they come up with more complex models of the disease, and they utilize that to make sure that you can represent the disease in an effective way. Okay, so another model that was created was called the SIRS model. Okay, so what this says is for some disease, after you have the disease, for some time you are recovered. You may not have the disease again. But maybe after 2 years, you again become susceptible. Some diseases are like that. Okay. So this SIRS model measures that. After an infected node recovers, it passes briefly through a R state and then it goes back to the S state. So a lot of diseases are like that. So you have immunity for maybe 1 year after you have the disease, but then the antibodies die down, you are again susceptible to the disease. Okay. And so initially some nodes are in the I state and all others are in the S state. And each node V that enters the state remains infectious for a fixed number of steps. During these times, they have the probability of passing the disease to the other neighbors. And after T1 steps, the node is no longer infected. It enters the R state for a fixed number of time. During this time, it cannot be infected with the disease. But after then TR steps, it again moves back to the susceptible state. Okay. But again, so that model has some problems. So people came up with more complex models. So this model, so how people try to test the efficacy of how good the model is, then when a disease happens, they try to utilize that model to predict the spread of the disease. So one model that has been found to be pretty good, it is called the SARE model. So it has the state from susceptible, you cannot be directly infected. So you from that state you come to a state called exposed. Exposed is that you have come in contact with someone who has the disease. So once you susceptible is any one of us, once you come in contact with the disease, you move to the exposed state. Okay, and from the exposed state, so if just because I have come in contact with the disease, maybe I won't get it. But then what happens is some of the people with a probability will get the disease. So that is the exposed state. And then there is a recovered state and there is an immune state. So this is something like having a vaccine, right? So if you have a vaccine, you can move up to the immune state. So that is another state. And in each state, you have things like exit. So exit means, so for example, in the infected state, what exit means is that you have, for example, died unfortunately for the disease. But for the other state, there may be a possibility that the person has moved from that area. So there are exit states in the other states also. But the exit state in the I state is the most meaningful one. It captures the death rate of the disease. Okay. And so how the SIR model works is that again we have dsdt equal to minus bsi beta si, and the exposed state is, now we are going into the exposed state, and the infected state is going from the exposed state. Okay, so this is how the SIR model is done. But obviously, this model is also doesn't capture everything. So people have created more and more complex model. But people have also tried to see exactly, use a model and see how it works in some actual disease. So, for example, this is a paper which looked into the Ebola virus that I think was common in Africa during the 2010 to 2015 time frame. They tried to see the SIR model and model how the disease is spreading through the continent. Okay, so okay, so so this is how. Uh, so they have, is interesting. So you see, they have also added a F state. Okay, so, and they have added a H case for the hospitalized people. So you can make the model more and more complex to take care of different kind of state a person may be in. But the most important thing to model is also these numbers, the beta, the delta, and things like that. So, for example, how do you know that what is the probability that if you are exposed, how many of that will get the disease? So, modeling these parameters like beta and all those are also very important to figure out how the disease. So, what people do is they look into the past history to see. So, for example, from people who are exposed, how many of them actually get the disease, and utilize that to get the parameters like beta and delta and things like that. Okay. So another model which was studied with some of the COVID viruses and was found to be good was this state called ACIQRDP model. So here they have multiple states. So S is again the susceptible states, I is the exposed state, then we have the infectious state, and then so we are assuming in this model that a person who is infected will be immediately quarantined. Okay, so you see that from the infected state, no one is going directly to recovery. They are going into the quarantine state, and from the quarantine state, they are getting into two states. So, what is the two state? One is that you can recover from the quarantine state, or unfortunately, you can die. Okay, so those are the state. And also another interesting thing you see on the other side is from the susceptible state, you are in a protected state. Protected state means that you have got the vaccine and things like that. So you are moved into the protected state. And then they have also various kind of equations. The equations will measure how you go from one state to another state. Okay, so for example, how is this from the susceptible state? What is happening? People from the susceptible state, they can move to the exposed state, or they can move to the protected state. Okay, so you can see that dsdt is alpha st. So from there, some people can move to the exposed state, or you can see that some people are moving from the susceptible state to the exposed state using probability beta t. Okay. Similarly, from the exposed state, people can move to the infected state, and or they can move back. Okay. Okay. So also the interesting thing you see is that we have beta ST by N. So why we have the ST and IT? Because person from the susceptible state can move based on if they're coming in contact with the infected state. So therefore, they have both the parameters together to figure this out. So this model was found to be good for some of the disease for COVID in China. So we had one student who utilized this model to predict the disease for in various countries. So, for example, in India and US and so on. So the bold lines are the ones which is still the data that we have, and utilizing that we try to predict how the disease will go after the training period. And in many cases, this model was used to was pretty good in predicting how the disease will go after the thing. So we used the data that we had to calculate the various parameters, and then what we did was then we tried to predict the going forward how the disease will go. So it was very interesting. But overall, during COVID-19, even though we had so many models, none of the models were really successful. So they none of them could do a really good job, and therefore, if this kind of epidemics happen again, I hope so. A lot of studies are going on, and hopefully, people can do a better job. And the interesting thing is that they didn't use any, so use various methods to calculate the various parameters, but maybe having more machine learning kind of things will also help in this. Okay, but this is a very interesting field of study. Okay, so the tendency of so oscillations is what the tendency of epidemic for certain diseases to synchronize across populations, sometimes producing strong oscillation in the number of affected individuals. Okay, so for example, measles and syphilis. So you can have this oscillation. Sometimes it goes up, sometimes it's come down, and so on. Okay, and what are the main requirements for this oscillation to happen for a disease is long range links. Okay, so what is long range link? So I think in social network there is this concept of weak ties and strong ties. Okay, so strong ties is that if you have a social network that is formed within your close circle. So for example, within your college or within your office and so on. So here there are people who are in close contact with one another. And a weak tie or a long range link is one. So for example, someone from US is visiting India. So that is a long range link. It's coming for some time, staying, and he's getting into contact with not all the people in this local social network, but some people. So generally what has been found, this long range links, they are the reason why this kind of oscillations can happen in your network. And also the temporal immunity. Okay, the immunity produces a network wide deficit in number. So if there is a temporal immunity, the disease may start going down, and then after the immunity goes, the disease may again spread. Okay, so people have done some study on the effect of these long range rings. So if the number of long range rings is very small, then there is no oscillation. But if the number of long range rings is high, there are a lot of oscillations in the disease. Okay. Another important thing that we need to look at for this kind of spreading of disease is how long you are in contact with a person. Okay, so if you are in contact with a person for some time and you get the disease after that time, then of course you have recovered before you have seen that person, then obviously you cannot spread the disease. So look into these two small simple social network, and the numbers in the edge reflects the amount of time those two persons are in contact with. Okay, so for example, you and we are contact within the time frame 1 to 5, and V and W are in contact with the person during 7 to 11. Okay, so what happens in this case is that you can pass the disease to V because they were in contact during 1 to 5, and then V got the disease maybe around 5 or sometime, and therefore it can pass the disease to W because it came in contact with W after it had got the disease. Okay, so it can pass the disease, and then again W can pass the disease to Y. Okay, because it was in contact with after it got exposed, then it got in contact with Y. But W cannot pass the disease to X. Why is that? Because W could get the disease between the times 7 and 11, but it came in contact with X before that time. Okay, and therefore it cannot pass the disease to X. Similarly, in the second diagram that you see, W came in contact with V and it could potentially get the disease between the time 12 to 16. Okay, but it was in contact with Y before that time and therefore W cannot pass the disease to Y. So, the time that you are in contact with the person and the duration of the disease, that also plays a very important role in how this epidemic passes on. Okay. So in larger networks, the effect of concurrency on disease spreading can become particularly pronounced. Okay. So I will let you. Okay. So as the final thing for this, so look into this diagram, social network diagram. Okay. Suppose you are studying the spread of a rare disease among a set of people pictured in the figure above. The contacts among those people are as depicted in the network with a time interval which shows the how long you were in contact with. We assume that the point of observation run from 0 to 20. So assume that initially S is the only individual who had the disease. So which nodes could potentially have acquired the disease at the end of the time?
Could you zoom on the graph?
Hmm?
Could you zoom on the graph?
How do I zoom? So can S pass the disease to you? Yes. Good. Can it pass it to W? Okay. Can you pass it to Y? No. Very good. Can W pass it to V? Yes. Very good. Can V pass it to Y? Okay. So therefore, what happens in this case? So the disease gets restricted to this part of the population. Now look into the second question. Suppose that you find that in fact all the nodes have the disease at time 20. You are fairly certain that the disease couldn't have been introduced in this group from other sources. And so you suspect that instead that a value you are using in the start or end is incorrect. Can you find a single number designating the start or end of a time interval that you can change so that the disease will pass through all the population?
So can you zoom back? We can increase the end time between V and Y. So
Exactly. You can, so for example, between V and Y, if you, so for example, instead of 5 and 9, if you make it 15 to 19 or just one value, so for example, instead of 9, you make it 12 or 13, the end time, so that will make it. Yeah. Okay. Okay.